is Kalyan Nadella. He's an electroacoustic engineer with Knowles, where he's served also as the lead of their balanced armature commercial team. Their balanced armatures are in some of the most popular IEMs that we find in the industry. They're a major provider for that. Today he's going to be presenting on some listening preference research that led to the creation of a brand new balanced armature called the Super Tweeter that is gives much higher extension towards the top of the frequency range. So please join me in welcoming him.
Thank you. Hello everyone, good afternoon, and welcome to my talk. So, as the title suggests, today I'll be talking about the Knowles earphone curve. So this is, in essence, a preferred listening curve based on our research. And today's slides, they're mainly based on the work done by my colleagues, Tom Miller and Christina Dunn. Unfortunately, they could not travel, so I'm presenting it today on their behalf. I'll be able to answer most of your questions, but if it gets really technical, then I'll definitely get your contact information and get you the answer that you're looking for. So without further ado, so the overview for today's talk is split into three sections. The first section, I'm going to give a brief history and also the motivation for the work that was carried out. Next, we'll spend a significant amount of time in the test methodology, where I'll be talking about the participants, the software, the hardware that has been used, and the double-blind test that we've conducted to get to the preferred listening curve. And finally, in the results section, I'll be presenting the curve and some of the salient features that we've observed from the research. And finally, I'll be showing the Knowles curve and then answering any questions that you have. So the goal is that by the end of the slide deck, we'll be able to come up with a preferred response curve. With that being said, let's look at the history. So we all know that in professional audio, when we have large loudspeakers in a room setting, we would like to have like a very flat preferred response curve. So what do we have here? Just for everyone's understanding, we have a normalized response on the y-axis and frequency on the x-axis. Most of you might know we typically want like a flat response. But what happens if we go to in-ear monitors or TWS earphones? In order to understand, as you all may know, Dr. Sean Olive worked over 7 years to come up with a Harman curve, like where he tested a wide-ranging earphones to come up with the most preferred listening curve that is called the Harman curve. As you can see, there is a slight boost at the low frequency and also a 3K boost that reflects the ear canal resonance. Most of you might know this curve, but I'm just showing it as part for completeness. But as Jude was mentioning yesterday, there is uncertainty in the high frequency region. And one of the main reasons for that is because the 711 couplers used back in 2013 were not accurate in this frequency range beyond 10 kilohertz. So as you can see, the Harman curve gradually rolls off past 8 kilohertz, right? So this gave us the motivation, hey, is there an unexplored region in this high frequency range where the users might prefer a higher output? Is there a preference in this high frequency region where more output is beneficial to the user's preference? So for our study, we tried to mainly focus on this high frequency region without touching any of the frequency range below 8 kilohertz. Because we don't want to change that the current industry accepts. We just want to focus on the region that's not been explored before. Another reason was that we started looking at some of the earphones that have been released in the market. And these new earphones, some of them which have high frequency extension for the performance, were getting higher user ratings for sound quality. So we have a case in point is some Anchor earphones, Liberty 3 Pro. These are the measurements done by the sound guys. We have the sound quality ratings on Amazon. And we also have a third-party reviewers for this particular earphones. The goal is not to look at specific earphones, but just to look at this high frequency content and its effect on user preference. At this point, I do want to mention that, as you know, Knowles designs and manufactures balanced armatures. We have full range devices, we have dedicated woofers, and we also have tweeters. So yes, we do have vested interests that, depending on the output, we might be able to sell more transducers. But as you can see, I'll present to you how we did the testing, and we took great care so that we don't bias the outcome of the results. So we tried to do a lot of double-blind tests so that neither the participants nor the testers knew what was being preferred by the users. So we'll get to that later. And finally, there was a recent article by Dr. Olive talking about the preference and based on age. So in terms of that, it's like as the age progresses, there is some hearing loss for humans. So that is reflected in the plot on the right. So the plot on the right, just to give a brief introduction, so you have the sound pressure level on the y-axis, frequency on the x-axis. Basically what it shows is hearing thresholds versus age group. The main takeaway is that when you look at the red curve, which is 56 to 65 years old, what it essentially says is what is the softest sound that this age group can listen to. It does not mean that it's the sound that they need in the earphone, because as you know, earphones produce quite a bit more sound than 50, 60, 70 dBSPL. They can provide almost 200 dBSPL. So it's not what they can listen, but what is the softest sound that they can listen. And the goal of our study was to see if this threshold has an effect on the preference. So we wanted to know if this diminishing listening capability has an effect on the preference of the sound curves. So with that being said, it comes to the overall objective for our study, which is to see if beyond 8 kilohertz, if there is a preference for users for high frequency extension. That's objective number one. The objective number two is to see if, based on the progression of age, if there is a change in that preference. So we try to answer those two questions. With that being said, let's go into the test methodology, where I'll be introducing all the parameters that we have considered for our tests. So first is the participants. So as we talked about, hearing ability is reduced with age. The plot that you see on the right is, in essence, the reference. It's the comparison between different age groups and the age group with the best listening, which is 0 to 21 years old, which have almost one of the best listening capability. So the curves here just show the difference between the reference group and all the other age groups. So when we had participants, so we had around more than 100 participants. So we got the participants in for testing, and we did a listening test. And based on their audiogram, we sorted them into 4 groups based on their listening ability. So now we had enough participants that we know fall in different age groups. So once we had these participants, next we wanted to get to the earphone. So that for the earphone, we have used an inbuilt, a hybrid demo earphone. The reason for this earphone was we wanted to get output all the way up to 20 kilohertz, because we wanted to make sure that our hardware could actually produce the sounds in which we are interested in. So we had a reference curve here. So the black is basically a constant voltage input out that we get from the earphone. And then we try to EQ it to a flat line before we put our filters and our boosts in for testing. For the earphone, you can also see we put a microphone. So we modified the earphone slightly to have a microphone put on it. The reason for that is we wanted to detect if there were any leaks when the participants were doing the listening test. Because you might all know that if you don't put in your earphones properly, if you have a leak, the experience is diminished. You're not getting the right balance of low frequency and high frequency because you'll be losing a lot of low frequency content if you have leaks in your earphones. So with that, with the hardware being set, we moved on to the couplers. So if some of you might have attended Jude's talk yesterday, he talked in great deal about couplers. So just to give a refresher, not all 711 couplers are identical. And to give a slightly step back view about the whole topic, 711 couplers are typically used to replicate human hearing in terms of how humans perceive sound. It is in terms of the response shape. As you can see in the plot below here, the typical one that was used in the previous studies was the blue curve, which is the traditional 711 coupler. As you can see, it has really high peak at 12 to 14 kilohertz. So this caused a lot of uncertainty because between different 711 couplers, this peak was never identical, and it was never qualified beyond 10 kilohertz. So for our study, since we're interested in this high frequency content, we used updated couplers. So you can either use the RA0401 or 0403 from Grass, or as Jude was mentioning, you also have BNK 4620. The main takeaway is that you need to use damped 711 couplers which are accurate up to 20 kilohertz. And if you want to replicate our study, we suggest you start with RA0401. So this is the coupler that we have considered. The other important thing, as Jude mentioned again yesterday, was the importance of ear canal length. So for our study, we have considered the metal coupler. So as he mentioned, the reference plane for 711 is somewhere around here. So we wanted to have consistent measurements and also accurate measurements, because of which we use the metal funnel instead of anthropomorphic ear. And one of the studies is shown here below, where when you change the ear canal length, the high frequency content varies significantly. The tube length determines what is your performance in the high frequency region. So in order to get repeatable results, in order to get consistent results from testing multiple times, we try to make sure to keep the length as short as possible, because we wanted to get a reference curve, and then we also wanted it to be repeatable. And then it's also important to insert the ear tip to the right extent into the 711 coupler. So this, we have also seen it while developing multiple earphones. Like when you don't have a proper and consistent test setup, your response curves can vary significantly. So with the hardware being set, we wanted to move to the music content. So we have the participant set, we have the hardware that we have used set. So for the music, we had a lot of questions that we wanted to answer. It's like, why are we coming up with this curve? Is it to understand what people listen to on a general scale? Or is it targeted to very niche, or like to audiophiles in the market? So after some discussion, we came up with a decision that we need to come up with a reference curve for the music that's consumed significantly, like to a larger extent in the market. So for that reason, we went ahead with the pop music, right? So I know that many of the people in the audience might not agree to it as the quality music, but that's what we have, and that's what we wanted to go with to see what is being consumed in the market. So we went ahead with the last 20 years. So we considered music in the last 20 years and randomly selected 10 songs each year from the Billboard's Top 100. So we came up with around 200 songs in the last 200 years. And then these 200 songs, we wanted to analyze what is the frequency content of these songs. So in order to do this analysis, we did some spectrum analysis in a 200 millisecond segments. So we took 200 millisecond segments in the song and then averaged the energy in that time domain, and then changed it to the frequency content. And then we use 1/12 octave in order to get higher resolution in frequency. And then to get the loudness perspective, we normalized it to a 1/3 octave. And once we analyzed all the songs, this is the plot that we got for the 200 songs. So what do we have here? We have the SPL on the y-axis, we have the frequency on the x-axis, and for all the 200 songs, this is the frequency content. They're all shown in the gray curve. The red curve and the blue curve are in essence the 95% confidence intervals for all of the 200 songs. So within this plus and minus 5 dB from the average of the black curve, all the songs that we've selected reside within the confidence interval. So you might say, oh, all the songs sound the same. They might not sound the same, but it is the frequency signature has a similar pattern for most of the songs. So there are also a couple of interesting features, right? We see there is a broad frequency content. It does not roll off at 8 kilohertz, and we have output content all the way up to 16 or 17 kilohertz. So this tells us that there is some content in this high frequency region where we are trying to measure and trying to figure out the preference. So for the songs that we have considered, we selected 4 songs for our blind listening test from all these 200 songs. So the way that we selected these 4 songs were, we wanted the songs to be as close as possible to the average, one. But then we also wanted the songs to be slightly different from one another. They should not be identical so that they bias the listeners to a particular curve. So we looked for some variation between the songs. And finally, we also wanted to have natural instruments in the song, because we wanted to know how the users perceive when they listen to natural sounds, because that's what we're trying to see. How is the natural sounds that are being replicated in the preferred listening curve? With that being said, let's look at the filters, right? So what do I mean by filters? Filters is that, as I mentioned, we're going to take the Harman curve up till 8 kilohertz, and we're going to add something from 8 kilohertz to 20 kilohertz. So we need to add a set of filters or boosts in this high frequency region. In order to do this analysis, we went through several iterations, several options for us to increase the high frequency content. So first we chose a straight boost and shelf filters, where it's basically a rising filter from 10 kilohertz all the way up to 20 kilohertz. What we realized is that if you use filters like this, it was very hard for us to get enough boost without putting too much gain. So we had to put significant amount of gain before the participants were able to listen to any difference. So we didn't go ahead with this kind of filter. What we went ahead with is a Gaussian filter, which is located at different frequencies, right? So we have a Gaussian filter, so that has a nice spread of frequency content. Next, we had to figure out which central frequency do we pick. So we did some studies where we figured out that if you use a frequency of 12 kilohertz or low F0, you'll be adding a lot of content less than 8 kilohertz, which we didn't want to do. And if you use a central frequency of 18 kilohertz, then you didn't have enough energy in the region of interest, which is 10 to 20 kilohertz. So we went ahead with a central frequency of 16 kilohertz. So that's one. Next is the Q factor, like how do we shape this Gaussian curve, right? So we looked at different Q factors, Q factor of 2, which is too broad, that was affecting a lot of low frequencies again, so which we didn't want to affect, which is in the gray curve here. It's affecting a lot of low frequencies. If you use a Q factor of 2, which is the blue curve, it makes the frequency content very narrow, so it does not give a more smooth profile to the audio signature. So we went ahead with Q of 4. So we select a central frequency of 16 kilohertz and a Q of 4. And then we have different amounts of boost. So these are our input variables for the users to select from. A Q of 4 and a central frequency of 16 kilohertz and varying amounts of boost. So how does this translate to the frequency response curve? So you can see all the boosts in the top curve here, where you have starting from 3 dB all the way up to 27 dB SPL of boost. And when you superimpose that with the Harman curve, you get all these different response curves. And this brings us to our double-blind test. So this is the Mushra test, which is the industry standard. So it's a multiple stimulus, hidden reference, and anchor. So what does it mean? It means that there are two sound curves that we know, which is one is anchor, which we know is significantly worse. It has a very low frequency roll off, and it sounds subjectively and objectively bad. Like most of the users will figure out that it's a bad listening curve, and it's also a way for us to figure out if the participants are paying attention to the sound curves. And then we have a reference, which is our vanilla Sean Olive Harman curve, and then you also have different curves with different boosts that are being played to the participants. With that being said, let's look at the user interface. So the user interface for the participants looks something similar to this. So we have 4 songs, as we mentioned before. So the user is played 30-second clips from the 4 songs that we have selected. And they have 8 options. One is reference, one is anchor, and 6 variations of this high frequency boost. And they need to rank these 8 filters from what they really dislike to what they really like. So it's a, you can change this options to your rating. So essentially we want you to rate the filters from what you really don't like to what you like. It's double blind because the user does not know, or the participant does not know what filter is being used. And also the tester does not know what is the order of the filters. And in order to randomize further, each song is played twice. So a total of 8 songs will be played, and the order of songs is jumbled. So they're not played in sequence. They're all jumbled to make sure that there is no learning bias to the participants. So the songs are jumbled, the filters are jumbled, and the participants need to give a scale from what they really dislike to what they really like. So once we got all the results from the participants, we analyzed the data and we found some interesting trends. So, and that I'll be showing you in the results section. All right. So before I jump directly into the results, I would like to introduce 2 different plots here. So the first one is the sound quality rating plot. We'll look at the results in a bit. So the main thing to focus here is the y-axis, which is the quality rating. So it's a normalized way to look at what the users are preferring. So it determines the percentage that the user prefers a particular filter compared to other filters, right? It's a relative scaling between one filter versus the other filter. On the x-axis, you have the different amounts of boost. Like, is it a 3 dB boost at 16 kilohertz? Is it a 10 dB boost, 15 dB, so on and so forth. And the plot on the right, it shows the equalization. Based on the boost, how does the equalization look like? So you have the normalized dB on the y-axis and frequency on the x-axis. So for each amount of boost, the plots look like the curves shown here. So for different amounts of boost, 12 dB is in the green color, 18 dB is in the purple color, and the red is the 21 dB of boost. So these are the different frequency responses that are played to superimpose on top of the music files. So the results from the audience, from the participants, look like this. So let's look at the salient features of the results. One is every age group preferred at least some amount of boost, right? So everyone preferred, so the age group from 0 to 35 preferred at least 12, and as we progress in age, there are different preferences for this boost at high frequency. So the first takeaway is every age group preferred a certain amount of boost. The second one is with the progression of age, with every 10 years of age, we see that a plus 3 dB boost is preferred by the listeners. So that's the second takeaway. With progression of age, people like to see more boost. And the third one is the amount of boost is not selective, in a sense that if you take, for example, 0 to 35 years old, yes, people prefer the 12 dB of boost, but a plus 3 dB or a minus 3 dB boost from this central location is still acceptable. People still liked it. It's not like they only liked a particular amount of boost and anything else they didn't like it. So there is a broad spread of what people liked. And the other important thing is we need to definitely mention what is the preference within the age group, right? So what we found is that even within the age group, although they preferred a certain amount of boost, there was a wide spread of preferences from the users. It means that although a certain amount of boost is preferred by an age group, even within that age group, personal preference plays a role in what is required or what is considered to be pleasant to the users. With that being said, let's move on as to how it will affect our designs, because we have just seen that a certain amount of boost is required, starting from 12 all the way up to 21 dB of boost. Yes?
Sorry, just real quick. How many participants was this?
Oh, this was more than 100, so around, we tried to get around 20 to 30 per age group classification.
Thank you.
Yeah, so now that we have seen that we want at least some amount of boost in our output, there are different ways to get this boost in the high frequency content. One way is to use amplifiers and increase the voltage in this high frequency region to get more output. But as you know, the high frequency has a lot of crest factor for the complex music. So sometimes there is a chance for the music files to be clipped, that is the signals to be clipped, causing distortion or uncomfortable listening experience. So we propose that it's better to use transducers with higher sensitivity in the high frequency region, rather than just use amplifier to boost your output in the high frequency region. And the other benefit of using transducers with higher sensitivity is that you tend to use less power. So you get more battery life if you're designing a true wireless system which is dependent on battery. So an example for this design, in order to demonstrate this high frequency extension, we built a reference earphone. So what do you see here? So this is essentially a hybrid earphone that we have built internally in the lab. So we had a dedicated woofer in the earphone to begin with, or we had a woofer plus tweeter. So tweeter, we used an internal Knowles tweeter for this. So the main takeaway is that if you consider the reference curve of plus 12 dB boost that you have shown in the previous slides, if you just have a dedicated woofer, you start having this roll-off at 8 kilohertz and not having enough high frequency content. But if you have a dedicated tweeter in your design, then it's very easy to attain this high frequency extension. From this starting point of the red curve, it's very easy for you to do your modifications or tune it to the curve that it's more ideal to you. Right? So if you see this as a starting point rather than an end-all point. So with that being said, I would like to end with this slide where we introduce the Knowles curve. So essentially what you have seen here is the 12 dB boost curve at 16 kilohertz. So as I mentioned before, we tend not to change anything up to 8 kilohertz from the Harman curve. And then what we are proposing is a minimum of 12 dB boost at 16 kilohertz. After that, any additional boost is based on hearing loss based on age, or it's from the user preference. You can scale it up or you can scale it down. So with that, I will open the floor for any questions.
Were the participants measured on their hearing loss before the test?
Yes, that's a good question. So When we brought in these participants, we first did a listening test, and based on the audiogram results, we sorted them into the age group based on their listening capability.
And when actually placing the monitor, did you guys have a way to measure the distance in the ear?
No, we did not have a way to measure the distance inside the ear. But what we were able to do is to choose the right ear tip. Like typically when you go to the floor, most of them will try to give you the most appropriate ear tip so that it's your best listening comfortable position. And from that, we are not really worried about what is the waveform that hits the ear. What we want to know is that given this reference waveform, what is the preference for it? Because we need to account for this variation in the participants. We can't shove the earphone to the same level in all the participants. Because that's not the way it works, right? Because we are designing one earphone that needs to work for all the variations in the participants. So we made sure that it was a snug fit. We made sure that there were no leaks, but we wanted the participants to be comfortable, like how they would typically listen to any of the earphones or the in-ear monitors.
These tests, did they listen to the whole song?
Sorry?
Did they listen to the whole song when they had the song, the test?
No, so so we selected like a 30 seconds interval where we tried to have the chorus part of it where they had the full extent of the frequency response curve that we saw. So we wanted to make sure that when they were listening to it, the full frequency spectrum was representative in that section. So 30-second segments of the songs.
Yeah, because from like a hobbyist standpoint, real high energy headphones are where most people would tend to find fatiguing headphones.
Mm-hmm.
So it'd be interesting to see like follow up on, you might be wowed by it in your little snippet, but 3 hours of that, is it too much?
Oh yeah,
type of thing.
yeah.
That'd be interesting to.
Agreed. So we didn't consider the time part of it, but rather a preference between the filters. But yeah, good point. Yep. It's you feel like you might feel tired. Is that what you're saying?
Yeah.
Yep.
Yeah.
Yes, sir.
So, did your audiograms go up to 20 kilohertz?
Yes. Well, they go up to 18 kilohertz, right? Based on the bands, but you can measure it all the way up till that frequency. Yes. So we did use the tester. So we actually tried to get the tones all the way up to that frequency. Typically in audiograms, they don't even measure in that frequency range. I don't think it's the incapability of the test system, but it's just probably not focused on.
Is this Harman target the IEM one, or is it the standard headphone target?
It is the IEM one, so
Okay.
that's why you see a slightly higher boost. Or not, it will be right around like 2 to 3 dB, but since you get like a 6 to 7 dB boost compared to 1 kilohertz, then it's IEM one.
Okay.
How were the participants chosen?
Sorry?
How were the participants chosen?
How were the participants chosen? So many of the participants were employees of Knowles, so we just asked for volunteers to come in. And this was, as you can know, this was during the pandemic in the last year and a half. So we used internal Knowles employees, but they didn't know anything about the test. As you know, it's a double-blind test. But we also had some visitors who have come over to do the test. So we had some internal, mostly internal, and some external participants in this test.
Did you think of having some experienced listeners, either with some standard test or a test that you make up, and then comparing the results between the two groups?
It's planned. It's not yet done, but we are talking with a research group in Australia to see if others can replicate our test. So we're always willing, if more people follow what we have done and do more tests, to come up with a better approximation for it. But yeah, we're looking into it, but it has not yet been done. But yeah, I agree to your point. We need more data points, right? Because yes, 100 is good, but the more data points, the better.
If
And having different backgrounds is also helpful. But
Right.
these are not trained participants.
Right. So you would expect that it would somewhat replicate largely what Sean Olive did, which is show that there wasn't a huge gap between experience and unexperience. And that would go a long way towards validating it with perhaps fewer data points.
I agree. Yes, I agree to your point. That's definitely we are looking into. Yes. Any other questions? Yes.
Sorry.
Oh, no, please.
Another question then. So your results would suggest that either earphone manufacturers or amplifier manufacturers should have not a curve, but a boost that you could apply individually, perhaps with a suggestion based on your age or something. And it would maybe be a fixed kind of boost, but it would be something like age-related or preference or something. Maybe you'd label it something else because you don't want to be ageist or whatever. But it would imply that the user should have control over this.
Oh, you hit on a very good point. So I think this brings us to one of the trends in the TWS, mainly, not really in the in-ear monitors, but mainly from the true wireless system, where the concept of hearing personalization is gaining traction. So hearing personalization, as you may know, is based on the listening capability of the user. So they can take an audiogram and feed it into the software, and based on the loss, it compensates for that loss in the earphone response in terms of equalization. And many of the manufacturers actually give the provision within the app to tune the high frequency content. They don't give by individual kilohertz, but they give you bands, like 5 or 6 bands that you can change the equalization to better match your preference. Yes?
How was volume control during the listening tests? I'm not sure.
We tried to, so the volume based on standard listening, like we try to do the 80, so we try to see what is the typical listening level, right, based on the international standards, and then we tried to make sure that every one of them had comfortable listening level. We allowed for slightly modifications, but then we noted it down to scale it down again later on. But then all the songs were equalized to the same loudness level, because we know when you change the loudness, sometimes there is this perception of things sounding better. So we wanted to make sure the sound level is same. So I would say close around 80 dB SPL, if I remember correctly. Like we try to normalize to the same overall amplitude for the songs.
I assume that normalization is done across all frequencies?
The 30-second clip for the overall loudness for the song, for the clip. But all the frequencies, we don't normalize all the frequencies to 80 dB SPL. It's we just scale it so that the overall energy content is still the same for that 30-second segment. We don't individually do the frequency, but then hey, do we do plus 5 dB for the whole song, minus 5 dB, depending on the recording, right? Because one artist might record in one level, the other artist might record it in a different level. So we wanted to have the parity when people were listening or the participants were listening to the songs.
And did the participants have control over that during the whole time, or is it just at the start?
For the audio, for the sound, that we asked them to do for the first time, like not keep changing in between. Typically, we gave them the freedom, but I don't think participants changed in between, because once they're comfortable with a particular sound level, they're stuck with that, because we made sure that between the songs there was no abrupt change in the sound level of the clip. So, yep, I don't think any of the participants changed. Some of them had some requests to increase or decrease the sound at the very beginning when they listened to the first song.
Do we have any more questions? All right, let's thank Kali.
Thank you very much.